Right now, nearly 25 billion kilometers from Earth, a small machine is drifting entirely alone in the dark. Traveling at 61,000 kilometers per hour, Voyager 1 is the farthest human-made object in existence. But despite its epic distance, the hardware on board is frozen in 1977. The 3 computers driving this mission share a total memory of just 68 kilobytes, less data than a single modern photograph. What keeps a machine from the 1970s alive in the freezing void of space is a unique power source, an RTG, or radioisotope thermoelectric generator. It produces electricity from the steady heat of decaying radioactive material. That radioactive decay is slowing down. Every year, the battery loses about 4 watts of power capacity. To compensate, engineers back on Earth have been forced into a slow retreat, permanently switching off cameras and sensors one by one, just to keep the core systems running. By the early 2030s, the power will dip below the absolute minimum needed to transmit data. After nearly 6 decades of communication, this machine will send its final ping back to Earth, and its voice will go silent permanently. The reason we launched this fragile hardware in the late 1970s comes down to celestial timing. NASA scientists noticed an alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that only occurs once every 176 years. This map illustrates the orbital maneuver they used to take advantage of that alignment. By approaching a planet from a specific angle, a spacecraft can steal a tiny fraction of its orbital momentum, slingshotting outward at a much higher speed toward the next target. This is known as a gravity assist. In 1979, Voyager 1 reached Jupiter, sending back the first clear images of the Great Red Spot, a massive storm large enough to swallow Earth whole. A year later, it arrived at Saturn, revealing the astonishing complexity of its rings. We saw they were composed of thousands of distinct icy ribbons. But Saturn's largest moon, Titan, held a dense atmosphere scientists desperately wanted to study. They steered Voyager 1 close, knowing the moon's gravity would violently whip the probe up and out of the flat orbital plane where the other planets reside. That single navigational sacrifice meant Voyager 1 would never see Uranus or Neptune. Instead, it was flung upward and outward, making it an object destined for the stars. Look closely at this diagram. In 2012, Voyager 1 crossed this outer line, known as the heliopause. This is the exact boundary where our sun's solar wind stops, giving way to the plasma of deep space. It even recorded the physical vibration of this new environment. Entering interstellar space sounds like leaving the solar system completely, but our star's gravity extends far beyond its magnetic shield. To find the true physical edge of our solar system, we have to pull back to the Oort cloud. This is an unfathomably massive, spherical shell of billions of icy comets and debris that encases everything else like a distant, frozen cage. Even at 61,000 kilometers per hour, it will take Voyager about 20,000 years just to reach the inner edge of this cloud, and another 30,000 years to punch all the way through to the other side. The territory governed by our sun is so immense that the fastest machine humanity has ever built will spend tens of thousands of years simply walking to the front gate. Long before it reaches that gate, we will lose it. When the battery finally drains those last few watts in the early 2030s, contact will break forever. But a dead battery does not mean a stopped spacecraft. Space is a vacuum. There is no air resistance and no friction to slow things down. Without power, Voyager will simply coast on its current trajectory, trapped at exactly 61,000 kilometers per hour. It will become a blind, deaf, and silent passenger hurtling through the dark. The silence of its radio transmitter marks Voyager's transition into its ultimate permanent form, the era of silence. This map of the Milky Way shows exactly where that silent journey leads. Voyager is not flying in a straight, infinite line away from us. It is locked into a slow, massive orbit around the center of our galaxy, taking roughly 220 million years to complete a single lap. Over thousands of millennia, it will occasionally drift past neighboring stars like Gliese 445, but the gaps between celestial bodies are incredibly wide. The emptiness guarantees the chances of Voyager actually colliding with another object are almost mathematically zero. If we fast forward 5 billion years, our sun will exhaust its fuel, swelling into a volatile red giant. It will expand far enough to incinerate the Earth entirely, erasing every physical trace of where we began. Meanwhile, safely coasting in the deep freeze of the galaxy, Voyager will fly on entirely undisturbed. It is humanity's most stubborn creation, guaranteed to outlive the planet and the star that forged it. Billions of years from now, the Milky Way will undergo a colossal merger with the neighboring Andromeda galaxy. As gravity slowly tears and recombines the billions of stars into a new, unrecognizable shape, a tiny, silent 1970s machine will ride the gravitational waves right through the center of it all. And bolted to its side, it carries a deliberate payload into that deep future, a 12-inch gold-plated copper disc. Inside is a time capsule of who we were. It contains sounds of ocean waves, birds, and children laughing. It carries greetings in 55 languages, including Hindi and Sanskrit, alongside a curated mixtape of humanity's greatest musical achievements. The reality of the cosmos is stark. The universe is incredibly vast and almost entirely empty, meaning it is highly probable no alien civilization will ever intercept this disk to decode our message. The Golden Record functions as a cosmic tombstone, an eternal, silent proof that on a small blue rock, humanity existed, and we dared to reach into the infinite. Voyager 1 launched as a permanent extension of human senses and identity, carrying our perception deep into the cosmic ocean. In March of 1979, the spacecraft reached Jupiter. The resulting images gave researchers a jump in resolution, roughly equal to upgrading from naked-eye moon-gazing to a high-powered observatory telescope. This projection map shows Jupiter's full cloud surface, as recorded by the probe. The data exposed a highly active global atmospheric structure, where high-altitude cloud bands and circulating currents interact to form complex, swirling vorticity. This image captures a plume nucleus near the planet's equator. The puffy cloud elements stretching across the frame resemble terrestrial cumulus clouds, providing raw proof of vertical convection and extreme weather in the Jovian atmosphere. As the spacecraft swung around to the planet's dark side, the cameras picked up diffuse auroras and violent clusters of lightning. The instruments even detected a thin, faint ring of dust encircling the giant. A flurry of activity broke out at JPL as scientists realized the Galilean moons were unique, distinct worlds, upending the idea of them as identical rocks. They spotted heavy cratering on Callisto, massive tectonic fractures across Ganymede, and extensive active volcanism on Io. The encounter proved that gas giants are dynamic, violent systems that behave as churning liquid oceans. After a 17-month cruise, Voyager 1 arrived at Saturn in late 1980. From Earth, the planet's rings had always looked like broad, uniform sheets of material. The probe's cameras immediately challenged that assumption. The broad, featureless bands actually consist of thousands of individual, narrow ringlets. The outer F-ring exhibited a strange braided pattern. 2 shepherd moons orbit right along this edge, using their gravitational pull to sculpt icy particles into wavy lanes. Saturn's largest moon, Titan, was a massive priority for the science team. To get a good look, mission planners routed the spacecraft on a precise trajectory to fly within 4,000 miles of the moon's surface. The cameras revealed an opaque orange haze layer, totally obscuring the surface. The instruments clocked the surface pressure at 60% higher than Earth's and found an atmosphere choked with nitrogen, methane, and complex hydrocarbons, a perfect mixing bowl for prebiotic chemistry. Flying that close to Titan required diving beneath Saturn's south pole. The resulting gravitational assist flung Voyager 1 out of the ecliptic, the flat plane where the rest of the solar system's planets orbit. This maneuver, known as the JST trajectory, made further planetary encounters impossible. It was a deliberate trade-off, losing the rest of the outer planets to gain an intimate understanding of one highly unusual moon. By February 1990, Voyager 1 was billions of miles away, speeding out toward the edge of the Sun's influence. Astronomer Carl Sagan had spent years campaigning for the team to send one final command: turn the cameras around and look back. The spacecraft captured a mosaic of 60 frames, known as the family portrait. Within it is the pale blue dot, Earth, appearing as a single point of light, barely a pixel wide, suspended in a scattered ray of sunlight. In August 2012, the probe passed the heliopause. Crossing this boundary between the heliosphere and the interstellar medium made Voyager 1 the very first human-made object to venture into the space between the stars. Today, over 45 years after its launch, several of its instruments are still returning useful data. Engineers estimate that the spacecraft will finally run out of the power needed to operate them around 2025. Once the power fades, it will coast silently through the vacuum. In about 40,000 years, the dead probe will pass within a couple of light years of the star Gliese 445 in the constellation Camelopardalis. Beyond the discovery of moons and rings, Voyager 1's legacy remains a profound perspective on our own fragility and the hope that our message in a bottle will one day be found.